A lot of equations that we see only have one variable or only have one letter, like this example right here, 3x minus 4 equals 11. And we know that we solve that by adding 4 to both sides, and then we divide by 3. So we get a solution that's something like this, x equals 5 in this example. But sometimes we're going to see equations that have more than one variable. Maybe they have an a and a b, or an x and a y. So one thing we'll see is that if we have two variables, or if we have more than one variable, then we need the same number of equations as variables. For example, what we're going to see today is we have two variables, x and y, so we're going to need two equations to help us solve that. And when we have more than one equation, we call that a system of equations. And when we find our solution, it's going to be two variables, x and a y, and we write it as an ordered pair, x, y. And when we talk about the solution for a system, what solution means is it's an ordered pair, x, y, that makes both equations true, that works in both equations. So for example 165, we're not trying to solve this. We're given a system. Here's our system. We're given a solution, and we're asked to show that it is a solution. So how we're going to show this is we're going to take our x and our y, this given solution, and we're going to substitute it into both equations and see if it makes it true. So for our first equation, we have 3 times x minus y equals 5. Now we just simplify. 3 times 2 is 6 minus 1 equals 5. 6 minus 1 is 5. So we end up with a true statement, 5 equals 5. So it works for our first one. Okay, we can't stop there though. We have to make sure it works in both of them. So the second one, x plus y equals 3. 2 plus 1 equals 3. Well, that's obviously true, so it works in both of them. So if it makes both true, yes, it is a solution. Okay, but we are usually only given the equations, the system of equations, and we're not usually given our solution. We're usually trying to find our solution. So here in this section, we're going to be finding our solution by graphing. So if we have two linear equations, y equals negative 1/2 x plus 3, y equals 3/4 x minus 2, we're going to graph each one on a coordinate plane. I'm going to graph this first one in blue, and notice I'm going to identify the important pieces. My slope is negative 1/2. My b is 3, so let's remember how we graph lines. B tells me my y-intercept. That tells me where to begin. So we begin at positive 3. My m tells me where to move. That's my slope. My slope is negative 1/2, so we go down 1, right 2. Down 1, right 2. I'm going to continue making points until I run out of room in both directions. So there's my first linear equation graphed. Okay, now we're going to do the same thing for the second one. I'm going to graph this one in green. The slope of this line is positive 3/4, and the y-intercept of this line is negative 2. So we begin at negative 2 on our y-axis, and we move up 3 over 4. We can see right there they share a point. That's going to be the important point. Up 3 over 4. We can draw our second line. And then our solution is the point that makes both equations true, the point of intersection. So we've got one point of intersection, we've got one solution, and that solution is the ordered pair 4, 1, positive 4, positive 1. If we wanted to check this, we could plug this point into both equations and just make sure it makes it true. But we can see it on our graph. That's where they cross. That's our intersection, so that's our solution. Okay, in example 167, we're going to do the same process, but if you notice here, these are not in slope-intercept form. So before we graph them, we're going to go ahead and put this in slope-intercept form. I'm going to do the top one up here. To start out, I'm going to subtract 6x from both sides, and I end up with negative 3y equals negative 6x minus 9. To solve for y, divide both sides by negative 3, and we end up with y equals, we're going to get positive 2x plus 3. So the slope of this line is positive 2. The y-intercept of this line is 3. We start at 3. We rise 2, run 1. Rise 2, run 1. keep going in both directions as far as we can. Draw that first line. Now we're going to do the same thing with our second equation. I'm going to move my x's to the right side, and I end up with 2y equals negative 2x minus 6. Divide both sides by 2 to isolate the y, and we end up with y equals negative 1x minus 3. Okay, so the y-intercept of this line is negative 3. The slope is negative 1. So I begin at negative 3, and I move down 1 over 1, down 1 over 1. Or up 1, left 1, up 1, left 1. We see that point right there, point of intersection. So I'm going to draw my second line. This right here is the point that we're interested in, so our solution here is going to be negative 2, negative 1. Okay, a couple more. If we look here, example 168, these are both in slope-intercept form already, so we don't have to solve for y. And one thing we may notice here is that we actually have the same slope. We don't have the same line, but we have the same slopes. So think about what that means for our line. Whoops. So this first one I'm going to graph in green. I begin at negative 4, and I'm going to rise 3, run 2. Rise 3, run 2. Up 3 over 2 in both directions. Okay, the second line, we have the same slope, but we're going to begin at positive 1. So we start at positive 1, we're going to rise 3, run 2. Up 3 over 2 in both directions. Okay, so notice what kind of lines we have. If we have the same slope, when we graph those lines, we end up with parallel lines. And we know that parallel lines will never cross no matter how far we go. So if we have parallel lines, if our solution is where they cross, obviously these never are going to cross, so we have no solution. So parallel lines signify that we have no solution to this system of equation. There's no x and y that will make both of these equations true. Okay, example 169 is going to be our other kind of special case here. These are not in slope-intercept form, so let's do that really quick. Our first one, when I move that 2x to the other side, I end up with negative 6y equals negative 2x plus 12. Divide both sides by negative 6, and we end up with y equals, this will simplify to be positive 1/3 x minus 2. Okay, the next one, if we do the same thing, minus 3x minus 3x, we have negative 9y equals negative 3x plus 18. Divide both sides by negative 9, and we end up with y equals, again, we have positive 1/3 x minus 2. So notice this equation are exactly the same. So it's like I'm graphing this first one. We start at negative 2, we rise 1, run 3, up 1 over 3, up 1 over 3. There's my first line. And if we were going to graph that blue line, we start at negative 2, up 1 over 3, up 1 over 3, up 1 over 3. So what happens here is these lines essentially intersect everywhere. So if we have the same line graphed on top of each other, our solutions are infinite solutions. That means that these cross everywhere on the line. So when we're solving systems of equations, we can essentially have 3 outcomes. We can have one solution where they cross at just one point. We can have parallel lines, which gives us no intersection or no solution. Or we can have the same line graphed on top of itself, which gives us infinite solutions.